So this is the last topic that I want to cover in this discussion of simple harmonic motion, and after that we will move on to a new topic. And okay, so the topic is about coupled pendulum. So it's basically a system of oscillators which are coupled through which are coupled to each other, and then we are looking for their coupled motion and evolution of that as a function of time. So there is a generalized theory which we can apply to all these systems. However, here I am going to take specific examples and then try to understand the main characteristics of these kind of systems, and I am focusing on two examples which are exactly whose analysis is more or less same. One is two masses connected via three springs, and of course we have simplified the system in the sense that the masses have the same mass m, and they are connected to springs k of spring constant k to the ends, and the coupling is through a spring with a spring constant k1. Right. This system is analogous to another system which you have seen and worked on in your physics laboratory, and that is of two simple pendulum coupled via again a spring of, let's say, spring constant k here, and here also the simple pendulum are exactly the same, mass m, length l, and they are coupled with a spring in the middle. Right? And as described here, the theta values under small angle approximation can the deflection angle theta can be converted into the displacement x, analogous to the previous problem, and that is how both the problems will have more or less the same solution. Okay. So now to solve this, what we have to do is we have to, first of all, we have to write down the equation of motion for the system. So let us say that the displacement of mass 1 is x1, displacement of mass 2 is x2. Then we know how what is the equation of motion for a mass connected to a spring or a simple pendulum. So using that, now we can write down the equation of motion. So for mass 1, this mx1 double dot is minus k of x1 because of the stretch in this spring, and k1 x1 minus x2, the stretch of this spring, right, which one can see will be simply x1 minus x2. Similarly, for 2, the equation of motion is again analogous to the previous one. So mx2 double dot equal to minus k x2 plus k1 x1 minus x2. Right? Okay. So these are the two equations of motion. Let's write down as 1 and 2. Right? And what one can see is the equation of motion is not. So now the equation which we actually easily solved previously, now it's not that simple because there are two variables involved in this equation. It's not a single variable second order differential equation. So we have to worry about how to solve this. Right? Okay. Now a way of solving this is to kind of decouple the equations. Right? And for that, what we'll do is, looking at these two, we can say that let's define new coordinates. So let's define new coordinates x as x1 plus x2 and x prime as x1 minus x2. Right? So what we are saying is we are defining a new coordinate for this system. x1 plus x2 defines one displacement, and x1 minus x2 defines another displacement. Right? Both are displacement coordinates defined like this. And now if this is the case, then we can see that x double dot will be nothing but x1 double dot plus x2 double dot, and x prime double dot is similarly x1 double dot minus x2 double dot. Right? So using this, what we can do is add 1 and 2. So we can add these two equations, and if you add these two equations, you will get m x1 double dot plus x2 double dot. So this will give us SHM x1 double dot plus x2 double dot is equal to minus k x1 plus x2, and let's take the minus sign here, minus k1. So x1 plus x2 and plus this one, so this basically simply goes to 0. Right? This term will not contribute here. So this is one equation, right? And now what I can do is I can use the familiar form. So I can use this here. I can write this down as x double dot plus, I'll use k by m, and again here x is equal to 0. And as you can see, now this equation looks much more familiar to us and we know its solution, right? So this is a second order homogeneous differential equation in a single variable, right? And we know how to solve it, or we have guessed its solution earlier, which does correspond to the motion. So we can just use the same thing. So I'll write this down in more nicely in the way that x double dot plus omega naught square x equal to 0, right? So this is my next equation number 3, right? And we know its solution. We can also, from here, we can also subtract 2 from 1, right? So if you subtract this from here, basically what we are going to get is x prime double dot plus omega naught square x prime plus a term which will be k1 over m x prime equal to 0, right? So yeah, so I have used k1 here, right? So if you subtract 2 from 1, then we get this, which you can see here, right? And now what I can do is I can define this k1 by m also as a frequency parameter. This is also a frequency, although it's not the natural frequency of this mass and this mass connected to these springs. However, this is also a frequency characterized by the spring constant of the coupling spring. So x prime double dot plus omega naught square x prime plus twice of, let's say, omega k 1 square x prime equal to 0. And since it's again only a single variable, I can write it down as omega 0 square plus 2 omega k1 square x prime equal to 0. And this is also a homogeneous second order differential equation whose solution can be formed. So this way, by defining these two variables which are related to our original variables x1 and x2 describing the motion of the system, we have decoupled our initial equations of motion. So rather than writing the equation of motion in terms of the variable x1 and x2, right, which are coupled to each other, because there is a spring which is coupling this, we change the variable, we take the total displacement or the difference of displacements, right? We define those as our variables x and x prime, capital X and capital X prime, right? And if we write down the same equations in terms of these two, then what we find is in terms of these two variables, the equations are decoupled, right? So then these two become our, so now these two are independent variables, right? And okay, so these variables x and x prime are called normal coordinates for these coupled systems. So every coupled system or every system of oscillators which are coupled to each other can be described in terms of such normal coordinates, And in some cases, it will be easier to find the normal coordinates. For example, here, just by adding, subtracting, you could find the normal coordinates. In other cases, it may not be that trivial, right? However, the normal coordinates will always exist, and we can describe the system in terms of these normal coordinates. And the frequencies, so the frequencies omega naught square and this one. So basically the frequencies omega naught and omega naught square plus 2 omega k1 square. These two frequencies characterize the normal modes of oscillation. And why they are called normal modes of oscillation? Because as you can see here, the normal coordinates x and x prime are making oscillations. So this is the equation of motion for a simple harmonic oscillator. This is the equation of motion for a simple harmonic oscillator. But they both are oscillating now with frequencies omega naught and square root of omega naught square plus 2 omega k square. Right? So these two frequencies, so these two are the frequencies or natural frequencies of these normal coordinates. So they describe the normal modes of oscillations. Right? Okay. Now we will look at it in more detail in the sense that we will see time evolution. We will write down the solutions for this and then get back the solution for x1 and x2. Right? However, before that, let me just make another remark here that so for a system of n coupled oscillators, and we will not worry about the proof of it here, right? However, it's important to just for time being is to remember this, that for a system of n coupled oscillators, for example, here we have two oscillators which are coupled. We could have a system where we have three masses connected to springs and then coupling between those. So a system of n coupled oscillators, there will be n normal modes, right? And that means n natural frequencies of oscillation, right? So okay. Anyway, that is a statement for time being, but I will not going to go into detail of this. Okay. So now let's come back to our problem and start solving the writing solution of these two normal coordinates. Now the solution for these two normal coordinates, so okay, we write down the equation of motion again. So we had x double dot plus omega naught square x equal to 0 and x prime double dot plus omega naught square plus 2 omega k1 square x prime equal to 0. Right? So if I have these two equations, I can write down now the solutions. So x of t, I write it down as some amplitude cosine omega naught t plus phi 1, right? Where x naught, capital X naught is the amplitude and phi 1 is the phase factor characterizing this oscillation initial conditions, and omega naught is the natural frequency for this particular coordinate. Similarly, x prime t will be x prime naught, the amplitude, cosine of now this frequency, so square root omega naught square plus 2 omega k1 square t plus phi 2. Right? So then this is the general solution for these two variables. Right? And this is exactly same as what we have done earlier. So we can write it down like this. And now further analysis of this problem will require us to input more information into the system. For example, if you want to find out what are x0, x0, x prime naught, phi 1, phi 2, then we need to know what are the initial conditions in the system, right? So let us do that. Let's describe this thing in terms of initial conditions. So let's say at t equal to 0, right? x1 is x10, x2 is x20. So the initial displacement of these x1 dot is 0 is equal to x2 dot, right? So the masses are displaced from the equilibrium position, but they are not moving. So they are, so at t equal to 0, they are just at their just displaced from the equilibrium position. Now using this initial condition, we can find out the constant x0 and omega naught. What we will get is x of t will be then, well, in this case this will be simply x10 plus x20 cosine of omega naught t, and x prime of t will be x10 minus x20 cosine of omega naught square plus 2 omega k1 square. Okay, so these are then the solutions with the given initial conditions for this system, right? Okay, and what I can do is I can also write down just to make the things look more symmetric. I can take this as omega minus, I can take this term as omega plus, right? Because this is a higher frequency, this is the normal frequency. So omega plus, omega minus, and then the two equations look exactly the same.